Good afternoon, everyone. Thank you for joining our technical webinar. Today, we are very pleased and very proud at Diana to welcome one of our long-term and very knowledgeable end user, Coen van der Vliet from Arcadis. Coen is working with our software for already more than a decade, not for say two actually. And today he's going to present some of the work he has done on one of the old bridges in the Netherlands. Before I hand over the floor to Coen, I just want to bring to your attention that, as usual, during this technical webinar, your microphone will remain muted to avoid any background noise disturbances, but you have the possibility to type your questions. There is a question box, and you can type the question over there. And I will keep an eye on the questions, and when I think that the questions are basically relevant for the whole audience, I will raise the questions to Coen at the end of the presentation. This session will be recorded, and after processing and validation by Coen, we will publish it on our YouTube channel, so probably early next week. So you will have the possibility to basically watch a replay of this session. Having said that, I would like that, all together, we welcome Coen for this presentation today. And we are very curious to hear the outcome of the work he has performed on this bridge. Coen, the floor is yours, so you can unmute your microphone.
Thanks, Jean-Claude. So today we take a look at a recent nonlinear analysis of an existing bridge that we performed using the Diana software. We performed this analysis for our client Rijkswaterstaat, and the analysis was a real team effort and could not have been done without each one's dedication. And special thanks go to Alicia Nesterenko, who actually did most of the modeling and the simulations, and she did it in an excellent way. Before moving on to the project, I'd like to introduce myself. After graduating as civil engineer with focus on concrete engineering, I started working as modeling engineer at Rijkswaterstaat, the Dutch National Road and Waterways Authority. As young engineer, I became familiar with nonlinear analysis of structures, mostly in concrete. And after almost 10 years in this position, I moved on to Arcadis, global design, engineering and management consulting company. At Arcadis, I continued the use of advanced finite element analysis, and I faced the challenges of doing this high-end work in a commercial environment. Last years, I've been involved mostly in reassessments of existing structures, tunnels and bridges. It would be hard to do this work without inspiring discussions with colleagues within the company and elsewhere. And therefore, I'm very happy with the Diana Users Association. And I'd like to take this opportunity to draw your attention to that user association. The association is an independent body that unites users from companies, universities, and research institutions in a firm and enthusiastic network. The Users Association organizes lecture evenings about nonlinear analysis in general and Diana analysis in particular. And we also collect user wishes in the so-called wish list that we share and discuss with the Diana AVA management. Being a member of the association enables you to contribute to the wishes and to prioritize the collected wishes. Members also get a discount on the fee of the yearly international user meeting. This year, the user meeting will be held in Valencia in September. If you're interested in the user association membership or in the user meeting in Valencia, please visit our website, dianausers.nl. And if you'd like to present your project or research work in Valencia, please reach out as soon as possible, because there is still some room for a few presentations. I'll start with a few words about the project. Where is it? What's the structure like? How was it built? And why do we actually need this reassessment? And then we will look at our approach, followed by a description of the model and the analysis. And after looking into the results, we end with the outcomes of the sensitivity analysis. The bridge is located in Amsterdam, shown here with its very characteristic canal network. Zooming in at the eastern part, we focus on the location where the Amsterdam Canal connects to the River IJ. In 1957, a road was built that crossed both waterways with two nearly identical bridges. The Amsterdamsebrug, it's the bottom one, and the Schellingwouderbrug, it's the top one. Both bridges have a tight arch as main span. It's built in steel, and long approaches consisting of concrete T-shaped girders. And here you see the long section of the bridge where you see the very long concrete approaches. The approaches consist of a number of sections, and each section is constructed as a continuous beam, composed of 5, 6, or 7 spans. The spans are made of prefabricated T-shaped pre-stressed girders, and initially these girders were positioned on temporary supports as isostatic independent girders, shown in orange here. In order to combine the girders to a monolithic continuous structure, coupling plates are placed in between the girders, shown in purple, above the supports. And these coupling plates are pre-stressed as well. And subsequently, the primary cross beams in blue were cast and pre-stressed. And finally, all parts are glued together with the secondary cross beams and the concrete cast in, shown in turquoise in the cross section. And this cast in fills all the gaps between the girders and the coupling plates. Transverse pre-stress along the full length of the bridge deck ensures that all these parts keep working together. And the spans of the governing section measure 22 meters, and the bridge deck height is 1.1 meter. I told you the girders are pre-stressed, and this picture shows the layout of the pre-stress tendons and the way they designed it back then. And it also shows the traffic load configuration used to dimension the pre-stress. It's a checkerboard of span loads. After having been in service for almost 50 years, the original steel bearings of the approach bridges were replaced by elastomeric bearings. The original bearings had been positioned under the primary crossbeams in between the girders, but the elastomeric bearings were placed under the girders themselves. Almost 20 years ago, the Dutch Road Authority started a huge campaign to reassess the structural safety of all their structures. The main reasons were the knowledge advances regarding shear strength and the associated change in design rules. Prior to 1974, shear strength was evaluated based on principal tensile stresses in the shear zone in the serviceability limit state. And for some situations, this approach proved to be too favorable. Starting from 1974, shear was evaluated based on shear stresses for the ultimate limit state, which yielded way less favorable results. As part of this campaign, the Amsterdamsebrug was evaluated using a linear quick scan method in which a unity check value of 1.85 was found for the fifth girder in the end span, shown in orange. And shear tension was the governing mechanism. Rijkswaterstaat asked us to perform a nonlinear analysis to analyze the failure behavior for this governing load position and to explore the margins in the resistance. And their hope, of course, was to find a unity check below 1 so they could safely state that the structure was reliable. And thanks to the quick scan results, we knew where, in what way failure was to be expected. And based on this knowledge, we defined our approach for the nonlinear analysis. Knowing that shear was the expected governing mechanism, we could use neither beam elements nor orthotropic shells. In order to account for both the shear failure and the load distribution in transverse direction, we needed at least shell elements for both the deck slab and the girder webs. We decided to go one step further and used solid elements for the governing girder in order to have a good representation of the effect of stress concentrations and the combination of shear and torsion. Solid elements have another benefit. They naturally reduce the effective span to the clear distance between the primary crossbeams. Using solid elements for the full model would require too much computational power. So we decided to use shell elements for all other parts, but use solid elements for the governing girder and the associated parts of coupling plates, crossbeams, and cast-ins. Based on previous experiences, we decided to model the pre-stressed tendons as accurate as possible, with each tendon individually modeled as post-tangent embedded reinforcement. This enabled both the good prediction of time-dependent losses and an accurate assessment of the contribution of inclined pre-stressed tendons to the shear capacity. All regular reinforcements were modeled as grids. It's an economic way of modeling them while being sufficient for the analysis. The vertical reinforcement bars are badly detailed. You can see it here. I hope it's clear on your display. It's only a very short anchorage length with hardly any proper hooks. So the vertical reinforcement can't really serve as proper shear reinforcement. And this grid modeling that we adopted enabled us to investigate this phenomenon in the sensitivity analysis in a rather easy way. Because of the complex phased construction with several changes in the static system, it was not possible to just model the bridge and increment the loads up to failure. We needed to include the construction stages in the model as well, and we used the famous phase module. We included a separate phase for each change in the static system, and even the grouting of the pre-stress got its own phase as it switches the bond conditions from no bond to full bond. In the very last phase, the time steps are followed by load steps to increment the loads up to failure. And let's look more in detail to the model. From the quick scan, we already knew the governing girder, the probable failure location, and the associated governing wheel load configuration. And this slide shows the top view of a 5-span section of the approach bridge. A first simplification was to ignore the horizontal curvature. And the client allowed us to model only a relevant part of the structure, and they suggested to model 3 spans with a symmetry boundary condition at the end, which means that we would place a symmetry boundary condition at this location. In order to be able to apply the live loads in a checkerboard configuration, we finally decided to place the symmetry condition halfway through the 3rd span. So we modeled only 2.5 span. The picture also shows the applied live loads. The orange shaded zones denote the distributed traffic loads. The purple zones denote the load on the bike lane, and the small orange squares are the wheel loads of the governing tandem system positions. In the lighter shades at the right side, the mirrored loads are shown, proving that we indeed model a decent checkerboard. As said, we modeled the 5th girder from the left side with solid elements and all other parts with shell elements. The pictures show how the solids connected to the shells. The right picture shows this connection at deck slab level, and the left picture shows the bottom side, where the solid parts of the crossbeams connect to the neighboring shell elements. So here you see the onset of the crossbeams and where they continue as shell elements. And this picture also shows the imprints that we used to apply the supports at the original and at the final positions. Our decision to model both with shell elements and solid elements gave us some things to think of. The first one was the linear elastic stiffness of the structure. In the first calculations, the solid parts proved to be stiffer than the shell parts, and hence the governing girder attracted more shear force than the neighboring girders. And of course, that doesn't help when you want to prove more strength. Where the shell girders connect to the shell crossbeams at their respective center lines, the solid girders just run up to the clear side of the crossbeam. So the shells connect to the crossbeams at the center lines, and the girder actually feels the crossbeam already over here. So it has a shorter effective span and thus behaves stiffer. We solved this issue by just increasing the width of the shell girder in the zone where it sits within the real crossbeam. So increasing the stiffness in that zone. The bridge contains several types of pre-stressing. curved tendons in the girders, straight wires in the coupling plates, and bars in transverse direction in the crossbeams and the deck. We modeled each individual pre-stress element with its appropriate curvatures. We used the option post-tangent reinforcement for all elements, with a realistic wedge shed for the tendons and 0 wedge shed for the bars. The wires in the coupling plates are actually pre-tangent, but they have such a short transfer length that we could model them as anchored post-tangent reinforcements with 0 wedge shed. The option post-tangent reinforcement allows the user to input the initial pre-stressing force, the friction properties, and the wedge shed, and it calculates the stresses in the pre-stress elements after immediate losses. The time-dependent losses consist of concrete creep and shrinkage on one hand, and steel relaxation on the other. The concrete creep is taken care of in the time-dependent analysis, but the steel relaxation is not. We decided to apply the expected steel relaxation as an a priori reduction of the initial pre-stress force, and we based our expectations on the Dutch guidelines for reassessments. About the finite element mesh, which is one of the most interesting things when it comes to finite element analysis. Defining the mesh properties is always a kind of a trade-off between accuracy and model size. There are clear limits. Elements smaller than the aggregate size don't make sense, and neither do elements in the order of magnitude of the girder height. But there is a lot to choose in between these limits. The Dutch guideline for nonlinear analysis of bridge girders requires at least 6 elements over the height of the structure. Another important criterion follows from the softening behavior in tension. Using a smeared crack approach, the shape of the softening branch is governed by the shape of the curve, the mode 1 fracture energy, GF, and the crack bandwidth, H. For the type of the curve, we used exponential softening. The fracture energy is a material constant, and it can't be changed. And it's denoted here with the shaded zone. It's actually the area below the diagram. And the crack bandwidth is dependent on the element size. The bigger the crack bandwidth, the steeper the post-peak softening branch, as this area needs to be the same. At a given value of the crack bandwidth, the softening branch becomes vertical. The nonlinear guideline recommends to use at maximum half the element size that results in a vertical downward branch. And for our case, this recommended element size would be 23 centimeters. We even used a slightly smaller average element size of 15 centimeters. And this gives us 7 elements over the girder height, which is deemed sufficient for describing the shear behavior of the beam. At the right side, you see a part of the finite element mesh, with the solid elements in yellow and the shell elements in gray. The orange symbols indicate the wheel loads when they are evaluated on the mesh. And we show them here spread either to the system plane of the shells or to the top surface of the solids. And we used the quadrilateral loads option for this, which allows you to define arbitrary rectangular load patches, and Diana translates these loads to appropriate element and nodal loads. It's a very handy feature. A second issue related to the choice for a combination of solids and shells was the connection between the two. Just choosing your node positions at corresponding locations is not enough, as that couples only the translational degrees of freedom, resulting in a kind of hinge between the shells and the solids. The shell elements have 5 degrees of freedom per node, 3 translations and 2 rotations, whereas the solids have only the 3 translations. Diana has a very handy feature for this. It's called automatic tyings. It's a strong feature, but it should be handled with care. The automatic tying allows the user to select which solid nodes are tied to the shell node. In this way, the automatic tying actually creates a rigid plane perpendicular to the shell plane, and therefore it prevents warping of the section in the solids for all the associated nodes. For pure bending, this is fine, but when shear should be transferred by the tied section, it behaves a tiny bit too stiff. A second and more fundamental difficulty is that it is impossible to use auto tying for a T-shaped section. Now, we had a lot of T-shaped sections in the bridge. Each crossbeam forms a T-shape with the deck slab. The nodes that are both part of the deck and of the crossbeam can't be assigned to two master nodes. And we decided to ignore one of the two masters for these specific nodes. And as these nodes do not sit in the outer fibers of the structure, the effect is not too big. But it would be very handy if the auto tie option was extended with this kind of T-shape option. About material behavior, one could talk either very long or very short. The short version is here that we based our strength on samples that were taken from the bridge a couple of years ago, and that we followed the Dutch nonlinear guideline for all derived parameters. But let's highlight a few interesting things here as well. For the analysis of failure behavior, it is important to use the actual concrete strength class, but creep and shrinkage need to be calculated based on the original strength at the time of first loading. So we calculated the initial strength back in time based on the actual strength, and we derived the creep and shrinkage curves on that initial strength. When assessing strength with a nonlinear analysis, it is important not to overestimate the ductility in the structure. And the steel rupture strain, the ultimate steel strain, is an important parameter for that. We decided to let the steel stress drop to 0 at rupture strain. And numerically seen, this is not a very good idea, as it results in the release of a huge amount of energy in an already heavily damaged system. But it will definitely result in bad numerical behavior, which in itself is a warning that results from these steps are unreliable. Using nonlinear analysis to assess the structural safety of a bridge comes with a challenge. We're utilizing the hidden margins that come with redistribution of forces, and we must be pretty sure about the reliability of the failure load that we find. In linear analysis, we very often use partial safety factors to deal with uncertainties in material and loading, but for a nonlinear analysis, it doesn't make sense to reduce the concrete strength on beforehand, as that might influence the actual failure behavior. Instead of accounting for uncertainties on beforehand, we apply the material safety afterwards on the resulting failure load using the global resistance factor safety format. In this method, the nonlinear analysis is performed with mean values for the material properties, and this results in the end in the mean value of the resistance of the failure load. The uncertainty with respect to material properties and to modeling is expressed as global resistance factor, and this factor is used to translate the mean failure load into the design strength. This global resistance factor depends on the material uncertainty and on the model uncertainty. For bending, the model uncertainty is small, 1.06, but for shear, a larger factor has been defined, 1.15. For structural concrete, the material uncertainty is defined as 1.2, based on the properties for steel, being the ratio between the mean yield strength and the design yield strength of the reinforcement. The total global resistance factor then becomes 1.38. So you need to be able to increase your loads beyond ultimate limit state with a factor of 1.38 before you can say that it's really safe. As concrete has a larger ratio between mean strength and design strength, we still need to reduce the concrete strength a bit on beforehand in order to be able to apply this same global resistance factor. So for concrete, we apply a so-called GRF mean, and it equals 85% of the characteristic strength. And in case you wonder if this is still according to the codes, this entire method is comprehensively documented in the FIB model code, and it's fully compliant with the Eurocode. Another challenge in a nonlinear assessment of a full structure is the fact that there's a lot going on in the structure, and not only in the location that in the end will be the failure location. We all know the textbook examples of a single simply supported beam failing in bending or in shear, and we can easily believe that those examples are performed with excellent numerical behavior and decent convergence. But in a full structure, there are multiple girders, each with its own amount of damage, and there's not only one shear crack, but also, and much earlier, a lot of bending cracks, that all influence the iterative procedures that we try to control based on the convergence behavior. All this scattered damage spoils the convergence norms, especially for energy. Anyone analyzing larger structures has experienced that convergence is a lot harder to achieve. And if there's no convergence, how reliable are the results? It actually means there's no real equilibrium in your system. To deal with this issue, you could use, for instance, multiple convergence criteria simultaneously. And always be careful with results from non-converged steps. A single non-convergence is not a real issue, but in case of a series of non-converged steps, you should evaluate the reliability of the outcome based on what you see in the deformed plot, and always check if material laws are still being obeyed. This actually is also a nice example of a topic that resulted in a user wish for the wish list I told you about in the introduction. Based on experiences like this, the wish arose to develop a more focused convergence check in which the user could denote a region of interest. It was placed on the wish list and prioritized by the community, and at present, the board of the Users Association is discussing this wish with Diana FEA for an eventual implementation in an upcoming version. When performing an analysis as this one, it's good practice to start with a linear analysis to be able to verify your model. It allowed us also to compare the outcomes with the quick scan in order to gain trust in the model. And after the model verification, we first ran the creep and shrinkage analysis. And based on the outcomes of this time-dependent analysis, we had to modify our assumptions for steel relaxation a bit. And with this correct model, we applied the creep and shrinkage analysis again, and we could increment the loads up to failure after that. And part of the reliability philosophy was to investigate the influence of certain parameters based on the sensitivity analysis. In the following slides, I'd like to present the results. Let's start with the creep and shrinkage outcomes. The creep and shrinkage analysis gave us good insight in the actual losses per part. It turned out that each part has its own amount of time-dependent losses from creep and shrinkage, and that these losses even differ between the prestress elements within one part, and also vary along the length. This variation is not that big, and the practical approach of assuming a certain amount of loss for the entire structure won't be far off. The question is how much that amount should be, but let's come back to that later. As engineers, we're used to load displacement diagrams that start pretty steep and then flatten after cracking and show failure at the end of a horizontal branch. For a creep and shrinkage analysis, however, a load displacement diagram turns out to be pretty weird. This is the load displacement diagram for this creep and shrinkage analysis. Maybe easier to read is the time displacement diagram shown at the bottom. From the start at point A, the pre-stressed girders creep upwards, so positive displacements. Then after application of more dead load, the creep displacement becomes negative, and at the very end, they are close to a resulting displacement of 0. So there is still a small positive deflection at the end of 100 years of creep and shrinkage. And then for the load incrementing part, we obtain our familiar load displacement curve again. It presents the total load applied against the displacements at midspan of the governing girder. In this case, it doesn't start from 0 displacement, but from the slight hogging that resulted from the pre-stress and the creep. And it also doesn't start from 0 load, as we applied already the serviceability load level of the permanent loads in the previous creep and shrinkage analysis. And this serviceability level of the permanent loads is denoted with this bottom dotted line here. All other dotted lines are several load levels from the serviceability limit state via the ultimate limit state and the global resistance factor level to, in the end, 2.5 times the ultimate limit state load level. In order to state that the structure is safe with sufficient reliability, the failure load should be above the level where the ultimate limit state loads are multiplied with the global resistance factor. So we call this level simply GRF. It's the yellow line in this graph. And from the graph, it's pretty clear that the structure has a lot of margin in the resistance. We could even increment it not to 1.38 times the ultimate limit state, but to almost 2.5 times the ultimate limit state loads. Several remarkable moments are shown in the graph. Until ultimate limit state load level, all steel in the model is still in its elastic range. Just before reaching the GRF load level, the reinforcements in the cast-ins start to yield. And just after GRF, the bending reinforcement in the girders starts to yield, followed by the vertical reinforcement in the girders. And all pre-stressing stays elastic until a load level of 2.5 times the ultimate limit state load. And as soon as the pre-stress in the girders and the coupling plates starts to yield, the failure mechanism is triggered and the load can't be incremented any further. We told about convergence behavior before. Actually, for this analysis, it was not too bad, at least up to reaching the global resistance factor load level. This graph shows the number of iterations per step. The first non-convergence occurs just after GRF load level, and it lasts 5 steps before convergence is established again. And then, when the pre-stress starts to yield, the second non-convergence occurs, and it's not re-established anymore. We still need to see the results to evaluate the reliability of the first series of non-converged steps, but this graph already gives some clue that the ultimate failure load is slightly lower than 2.5 times the ultimate limit state loading. In the following slides, we see the development of cracks in the girder. And please note, the structure is shown upside down. So we are looking at the bottom side of the girders. And the governing girder, this fifth girder, is shown in red. And the very first bending crack occurs just after reaching the ultimate limit state load level. And more or less together with the first bending crack, the shear tension crack arises in the shear zone close to the first intermediate support. It proves to be the onset for our critical shear crack in the end, but at this load level, it's not critical at all. At global resistance factor load level, a lot of bending cracks have developed. Our shear crack has developed a little further, and in the neighboring elements, in the neighboring girders, also a tiny crack becomes visible. Not earlier than at twice the ultimate limit state load, the shear crack has developed to a serious crack. Apparently, the reinforcement and the pre-stress were sufficiently effective to control the growth of this crack. The bending zone now shows a completely developed crack pattern, and when you realize that each of these cracks opens or closes with any load increment, you can imagine that all these cracks together could influence the convergence norm significantly, with so many bending cracks against only one single critical shear crack. The color scale of these pictures is changing from picture to picture based on the amount that has to be shown, which gives also a clear view on what crack is actually dominating. And at 2.4 times the ultimate limit state load, the shear crack has finally become wider than the bending cracks. We see these shear cracks in all girders now, more or less in the same shape and at the same location, close to the first intermediate support. And the crack strain values now range up to 2.6%. It's shown in the box over here and also over there. And then suddenly, 2 steps later, the crack strain has increased with a factor of 10 to 22%. For elements of 15 centimeters, as we have in our model, this 22% means actually a crack width of, say, 3 centimeters. This coincides with this horizontal branch in the load displacement diagrams, and for sure, you can state at this load level, the structure has failed. But let's have a closer look at the crack development in the governing girder. Here it's shown in its normal regular position, so not upside down anymore. The shear crack arises more or less together with the bending cracks, but up to a load level of twice the ultimate limit state load, the bending cracks develop much faster. After that load level, the damage behavior gradually changes from bending to shear. And the final failure mechanism is triggered by yielding of the girder pre-stress. At that moment, the critical shear crack can't be controlled anymore and growth in an unrestricted way. That the failure mechanism is definitely shear is clearly shown with this series of deformed plots from the zone close to the support. As soon as the pre-stress yields at 2.45 times ultimate limit state, a small kink is seen in the bottom face of the girder, just next to the supported face. In only 2 steps, this small kink becomes a complete offset, indicating that the girder displaces independent from the support. Based on these deformations, I think there's more to say about the mechanism though. And let's have a look at the compressive strut. The pictures on this slide show the principal compressive strains in the governing girder. When the shear crack develops, the vertical loads on the girder are picked up by the vertical reinforcement and the inclined pre-stress elements. When the vertical reinforcement yields, all remaining load increments are taken by pre-stress only. And when the pre-stress starts to yield, there's no structural element left to pick up the load. So the compressive strut that runs parallel to the shear crack tries to take over, but it has no capacity left. Its compressive strains quickly increase, while the stress rapidly drops due to compressive softening. And it's the blue zone in the bottom plot that shows that in only 2 steps, the full compressive zone fails. In order to still get a better understanding of the failure behavior, we also made another diagram. It's a shear force against shear displacement plot, shown below. Along the horizontal axis, the vertical displacement at the end of the critical shear crack is plotted, and along the vertical axis, the shear force transmitted by that section. It's interesting to see that the shear force can be increased up to a certain step, and it turns out that this step is the last step before yielding of the pre-stress elements in the girder. In the remaining 2 load steps, the shear force decreases while the load is still being increased. And this means that the neighboring girders take over here. It should be said that these load steps didn't converge at all, so the results are not reliable, but the total set of results, so all the pictures of the deformations and the strains and stresses, the total set of results of these steps is still pretty convincing about the actual mechanism. Now we got a clear insight in the behavior and in the failure load and in the mechanism. We wanted to determine the influence of those parameters that we actually knew not too much about. First, we wanted to know whether our accurate creep and shrinkage analysis really made sense. Would we find different results when we applied the calculated losses at once on beforehand? The next 2 variations had to do with the effectivity of pre-stress. First by increasing the losses with 50%, and then by reducing the initial pre-stress with 10%. Variations 4 to 7 all had to do with the crack pattern. In our reference calculation, cracking started pretty late, but in case cracking would start earlier, would it influence the failure load or the failure mechanism? We reduced the tensile strength in the shear zone based on the presence of a compressive strut, and we also reduced the tensile strength in the entire model. After that, we forced the settlement of the second intermediate support, and we pre-cracked the governing girder based on a more bending-focused traffic load position. Variation 8 combined the most influential variations of the 2 series before. Variation 9 was born from curiosity. In our reference analysis, we assumed a smooth and steady execution in which the changes in the static system rapidly followed each other. But when creep and shrinkage of the girders could occur for the biggest part before application of the cast-in, would that influence the outcomes? And the final variation had to do with the poor detailing and the poor anchorage of the stirrups. We reduced the cross-section of them with 75%. The first variation, which was to apply the effect of creep and shrinkage directly on the initial prestress, clearly shows that the advanced calculation of creep and shrinkage itself does not add to the failure behavior of the structure. But it should be said that we still used the losses that we calculated with the advanced creep and shrinkage analysis. An interesting alternative variation would be to just assume a certain loss and apply that on the initial prestress. We didn't do it so far, maybe in the near future, but looking forward to this kind of outcome. For all other variations, we incremented the loads up to twice the ultimate limit state values, so not up to failure. This plot shows the outcomes for variations 1 to 3, together with the reference calculation that is shown in red. Apart from some horizontal shifts in the curves, the behavior is completely identical, which means that the effective amount of prestress has no significant influence up to this load level. Reducing the tensile strength in the shear zone results in a somewhat faster development of the shear crack, but at twice the ultimate limit state loads, the reference calculation in the top right picture and the variation, the bottom right picture, show the same behavior. So also no real influence. Preloading and pre-cracking the girder with a traffic load at midspan gives the bending crack pattern a head start, so there's more deformation at the beginning. But again, at twice the ultimate limit state load, there's no difference anymore between the reference analysis in red and the variation shown in green. When we added a waiting time of 1 year before activating the cast-in concrete, we found much more cracking in the cast-ins. So the reference shown here, hardly any cracks in the cast-in concrete, and the variation 9 with a huge amount of cracks in these cast-ins. This is logical because now the cast-in starts to shrink when all other concrete parts had already had almost their full shrinkage. The cast-in shrinkage was fully restrained now and resulted in severe cracking. Having said that, the behavior up to twice the ultimate limit state load was similar to that of the reference calculation. The 10th variation finally had to do with the effectivity of the vertical reinforcement. We reduced the amount of reinforcement with a factor of 4, and at the end of the analysis, at the load level of twice the ultimate limit state loads, the shear crack appears to be more localized, which is logical as there is less reinforcement to close it. And the shear force shear displacement curve shows an increased development of shear deformation at the end of the analysis. We didn't run the analysis up to failure, so we must be careful to say something about the failure load. But if I had to bet which variation is the most influential for the failure load, I would select this one because of the increasing speed of shear crack opening. This graph shows all shear force shear displacement curves together. And apart from the horizontal shift due to different onset of cracking, etc., no significant differences are observed before a load level that's way beyond the required level GRF-ULS. This strengthens our conclusion that the structure has much more margin than found with the linear elastic quick scan. Let's wrap up. In a regular linear elastic reassessment, the development of a shear tension crack means that the ultimate capacity has been reached. In our nonlinear analysis, however, there is much more resistance against shear forces due to the mobilization of resistance in the inclined pre-stress elements. The unity checks drops from 1.85 to 0.56, which means that the structure is more than 3 times as strong as initially thought. It is important to mention that this outcome primarily applies to this specific structure and doesn't say anything about nonlinear analysis in general. It could have been the other way around, when the nonlinear analysis finds failure mechanisms that remain hidden in the linear analysis. But for sure, it's true that the nonlinear model comes closer to the real behavior of the structure And in our case, this turns out to be beneficial. So far, the main conclusion. And let's end with a few lessons learned. We performed an integral calculation of several spans of the bridge in order to find that the suspected governing girder was indeed governing, and that redistribution only occurred after failure of the governing girder. So in hindsight, the added value of the integral calculation was limited. Knowing what we know now, we could have found the same results with modeling only this governing girder over 3 spans. The sensitivity study showed hardly any variation in outcomes. Looking at the bright side, this means that the outcome is not too sensitive for uncertain parameters. But one might ask whether we shouldn't have varied other parameters, like the yield strength of the prestress. I guess we would have found more influence there, but as the yield strength itself is a well-defined parameter, this argument proves again the reliability of the analysis outcomes. I already mentioned the auto-tying option. It's useful, but it would be even more powerful if there was a solution for T-shaped connections. And finally, we used 3-dimensional elements to model the governing girder and used an advanced way of calculating creep and shrinkage through time. But in our case, the solid and shell parts behaved in a similar way. Does this mean that I won't use solids for this kind of analysis anymore? Not really. It fully depends on the situation at hand. There was also no difference between the advanced and simple creep analysis outcomes, and still the advanced creep analysis proved very useful to determine the actual time-dependent losses. So next time I might do that again. I'm coming to an end. Looking back at this project, I'm still very happy with the approach we chose and with the learning experience that it actually was. I want to express my thanks to the entire team. Sometimes nonlinear finite element analysis is hard labor, but very rewarding in the end when things come together. I wish you all good luck using nonlinear finite element analysis, and don't forget to enjoy. Thank you.
Thank you very much, Coen, for this very nice and very comprehensive presentation. That's nice to see the application of Diana to a project. I may comment on the auto tying. As you mentioned, there were this limitation. I'm pleased to tell you that this is now basically available in the Diana 10.9 version that we are going to release before summer. So within a month, 1 month and a half, you will have the possibility to try that in our new version. So
that's great. Thanks.
I hope it will please you.
Of course.
And let me quickly see. I see that there is a question from Casper, so I don't know if you can answer it. Have you considered the ECOV method over the GRF, and what were your considerations to choose GRF method?
That's a good question. For those who don't know, ECOV, estimated coefficient of variation, is another safety format where you apply 2 analyses. So one is analysis with mean properties, real mean properties for the materials, and the other one using characteristic properties of the materials. And the ratio between the resistance, the mean resistance, and the characteristic resistance actually gives you the basis to calculate the design strength. I like that one more, but there are a few reasons why we didn't choose this one. The first one is that the GRF is more compliant with Eurocode. The second one is that this Dutch nonlinear guideline for nonlinear analysis favors the global resistance factor method. So we had to, both documents are part of our contract, so we should have very good reasons not to use it. And the final reason is actually, yeah, maybe not the best reason, but doing two analyses is actually more expensive in computational time than doing one analysis. This is one of the things that I mentioned, doing nonlinear analysis in a commercial environment. In the end, there are deadlines and timeframes, and somewhere you should do some concessions. Maybe it's not the best answer, but at least this were our considerations. And I fully agree that ECOF in itself would have been a good safety formula to use here, provided that the failure mechanism doesn't change between the mean properties and the characteristic properties. If there's a change in failure mechanism, you have something to explain and to think about.
Thank you.
Does this answer the question?
I think so. Let's see if Casper get back to us. There is one more, which is a little bit more general, I would say, and yeah, maybe this you can base your reply based on your experience. Is high number of iteration for conversions good or bad? This is a question.
Once again,
is a high number of iteration for convergence good or bad?
Yeah, this is the question sounds pretty simple, but it's a very difficult
one. Yeah.
It all has the number of iterations that you need is dependent on a lot of things. It's dependent on the iterative procedure. So when you do a full Newton-Raphson iteration, you will generally find less iterations up to convergence than using modified, for instance. When you need a lot of iterations to find convergence, actually I tend to believe that the iteration that gives you convergence is kind of a lucky shot. So if your structure doesn't reach convergence in a limited amount of iterations, it's actually already saying something about the damaged state of the model. Of course, I prefer to have convergence within, say, 25 iterations or so. And I think default Diana gives you 10 iterations. But in the end, I'm happier with 99 iterations to get convergence when I selected 100 to break off the iterative procedure, then that I would have had convergence at 26 iterations, but I stopped after 25. So in the end, you need to find convergence somewhere. But this is typically the thing that I would like to avoid with this focused convergence thing that I talked about. So the high number of iterations is, in my opinion, an indication that there's a lot going on in the structure at a lot of places, and not necessarily being your failure location. If you have one clear failure location and nothing happening elsewhere, then normally you won't need this many iterations. And if you need many iterations, it's because there's a sudden change in something. So a sudden crack opening, then you have one step that doesn't find convergence, and then the next one picks it up again.
Well, thank you for your answer, Coen. And I may say that, yeah, there's no general recipe for that. I can say to Swastik, who was raising the question, that this is one of our course topics. So we have a course end of May online. So if you want to join the module I2 about this nonlinear iterative procedure, this is something we discuss. But as Coen mentioned, yeah, we cannot draw any standard conclusion. So it's also based on the experience you developed with nonlinear finite element analysis. Next to that, Casper says thank you for your previous answer to the previous question. So he was happy. And I don't see further questions so far. So I think we will be able to end this session. So I would like to thank you one more time, Coen. Really, we are very happy and very glad that you could give us this nice presentation. I think it was very well received. There was a lot of interest. So thank you for your presence and your time. It was very much appreciated.
Welcome.
And
it was my pleasure.
thank you. And I would say that within a week, this recorded session will be online after approval of Coen, of course. I'd like to invite you all to keep an eye on our website because there are more events coming. I think you can already register for the release webinar of Diana 10.9, which will be late June. And as I mentioned, there will be an online course starting on 27th of May. We still have a few seats available, so if you want to join, you still have the possibility to register. But generally speaking, keep an eye on our social network, on our website. There are always something going on. So if you want to be up to date, just keep an eye on that. So I'd like to thank you all for attending this technical webinar, and I hope to see you soon in one of our events, online or physical. Thank you all. Bye.